A hot air balloon is rising vertically at a constant rate of 10 feet per second. A car is driving on a straight road toward the point directly beneath the balloon at a rate of 30 feet per second. When the car is 100 feet away from that point on the ground, and the balloon is 50 feet above the ground, how fast is the distance between the car and the balloon changing? At this moment, is the car getting closer to or further from the balloon? Okay, let's draw a little picture. As usual, 100 feet, 30 feet per second, 50 feet, 10 feet per second, distance A. We'll call this t equals 0. Got the car going over here at 30 feet per second, the balloon going upward at 10 feet per second. It's 100 feet away from the point below the balloon is 50 feet up. And what's this distance A? Let's first try to get a good estimate of it by just looking at a little bit ahead and behind in time. So let's try t equals negative 0.1 and 0.1. So the objects are moving at 30 feet per second and 10 feet per second. So if we only take 1/10 of a second, they won't have moved very far. So it probably will be close to the final answer. So whatever we get from this, looking at these small steps, will be close to the final answer with calculus. At 1/10 of a second before t0, this distance will be, let's call this distance x and this distance y. At t equals negative 1/10, x will be equal to 103 because the car is going at 30 feet per second. 1/10 of that is 3 feet per second. So 1/10 of a second ago, it's 3 feet further back. Similarly, y is going to be 49. In that case, the distance A will be the square root of 103 squared plus 49 squared, which equals approximately 114.1. At t equals 0, x equals 100 as defined, y equals 50 as defined, and at t equals 0 equals the square root of 100 squared plus 50 squared, which equals approximately 111.8. This will give us a pretty good idea, but we can do one step more to get an idea of how fast the rate of change of A is changing itself. At t equals 0.1, x will equal 100 and x will equal 97 because it's gone 3 feet forward. Y will equal 51 because it's gone 1 foot up in 1/10 of a second. A will equal the square root of 97 squared plus 51 squared, which is approximately equal to 109.6. So we can see from 1/10 of a second before t0, the distance was 114.1. At t0, it was 111.8. And at t equals 0.1, it was 109.6. This gives a change from here to here of 2.3, and from here to here of 2.2. So this is in 1/10 of a second. So we know in 1 second it will go 10 times further. We have dA equals 2.2 dt equals 0.1. It's actually negative, it's going down. So, or delta A, delta t will then equal 23 or 22, depending on which of these you choose to. So we should expect the final answer should be around 22.5, because 1/10 of a second before, it's going about 23 feet per second, the change in A. 1/10 of a second after, it's going about 22. So you should expect it to be around 22.5. Okay, now let's get into the actual calculus. But right before we do that, time for a brief astrophotography break. That comet that we've all been hearing about, I can see it, and I'm going to take a picture of it. Pretty cool. Back to work. So A, what does A equal? A equals the square root of x squared plus y squared. We want to find how A changes with the time. So we want to find dA dt. A is related to x and y, not t. So how can we get x and y in terms of t? Well, at t equals 0, x equals 100, but it decreases by 30 per second. So x equals 100 minus 30t. Y, similarly, at t equals 0, is 50, but increases by 10 per second. So y equals 50 plus 10t. And then we can write this out. A equals the square root of the sum of 100 minus 30t squared and 50 plus 10t squared. Let's try to simplify this a little bit. So expanding first, we get A equals the square root of 10,000 plus 900t squared minus 6,000t plus 2,500 plus 100t squared plus 1,000t. Then we can add combine like terms equals the square root of 12,500 plus 1,000t squared minus 5,000t. This isn't written out in proper order, but we can ignore that. Okay, so this is A, but what is dA dt? Well, we can take the derivative of this. This can be rewritten as A equals, it can be rewritten as 1,000t squared minus 5,000t plus 12,500 all to the power of 1/2. Taking the derivative of this, we can just use the chain rule. So this will equal the derivative of the inner argument times the derivative of the outer argument. This equals 2,000t minus 5,000 over 2 times the square root of the same thing over here. Okay, so this is the derivative, but we want to know the answer for t equals 0, so we can simply plug in 0 here. All right, this gets a lot canceled out. That goes away, that goes away, that goes away. Then we just have, we can simplify this a little bit further maybe. Pushing the 2 into the square root. And we also push like a 10 in, another 10. Then we get 50 over the square root of 5. Or negative 50 over the square root of 5. And this equals approximately negative 22.361, which is around the 22.5 that we sort of estimated. And we'd see it's negative, so the car and the balloon are getting closer together, as you would expect, because the car is going faster towards it, while the balloon is going slowly away from the same point. This is an improper square root, but I don't believe in that rule.